Intermediate Algebra Section 1.7. We now study scientific notation, so named because of its usefulness in work with the very large and very small numbers that occur in science. And by definition, scientific notation for a number is an expression of the form n times 10 to some power, where n is in decimal form and n has to fall between 1, including, but less than 10. In other words, it has to be a single digit between 1 and 9, and m is an integer that the power for 10 is raised to. And let's take a look at converting some numbers into scientific notation. So here we have 125. The decimal is here, and for it to be in true scientific notation, we need to have only one single digit between 1 and 9, inclusive, to the left of the decimal place. So we need to move our decimal 1 power of 10, 2 powers of 10. So an equivalent would be 1.25 times 10 to the number of decimal places that we moved our decimal place, and it was 2. Now we could think of this another way of simplifying this is to have taken 125, and to get the decimal there, we would have had to divide by 10 to the second power. In other words, divide it by 100 to get our decimal there. But to maintain equality, since we're dividing by 10 to the second power, we would have to multiply 10 by the second power. This is truly what scientific notation is doing. So our 125 divided by 100 would give us the 1.25 times the remaining 10 to the second power. After we've been introduced to scientific notation, we understand the concept of the dividing and representing the equivalent of multiplying. So here in this next example, the decimal is at the far right of our number. We only want one single digit to the left of the decimal, so we need to move 1, 2, 3 decimal places. In other words, we're dividing by 10 to the third power, or 1,000, and to counter a division we multiply, so we end up with an equivalent of 3.42 times 10 to the number of place values to the third power. In these next two examples, we have small numbers, and to the left of the decimal we have 0. For scientific notation, we want a single digit 1 through 9, so we need to, in this case, multiply by a power of 10. That doesn't do it, and another power of 10. And to counter that multiply by 10 to the second, we divide by 10 to the second. Let me write that out. So here was our original number. We're going to multiply by 10 to the 1, 2, or second power. If we multiply this number by 100, it'll move our decimal over 2 places. So it's now in scientific notation. However, we can't just arbitrarily multiply by 100. To counter that, we'd need to divide by 100, or 10 to the second power. Simplify in the numerator, we end up with over 2. Let me do the multiplication. We end up with a 2.2 when we multiply by 100, and that takes care of that first 10, and we have a divide by 10 to the second, which we can bring to the numerator as 10 to the negative 2. Again, as we become familiar with scientific notation, when you are going from a small number into scientific notation, you end up with negative powers of 10 to represent small numbers. So we moved it over 2 to the right, and we can express that as 2.2 times 10 to the negative second power. In this next example, we're moving our decimal over 2, and another 2, and another 2 to finally have a non-zero number to the left of the decimal place. We have 4.53 times 10 to the negative, how many? 2, 4, 6 places. And again, we could verify it similarly to the actual definition of scientific notation. From here, can you go the other direction? If you're given a number in scientific notation, can you convert it to standard form? And because we have 2.04 times 10 to the third power, and our number system is based on decimals and powers of 10, it means all we have to do is move our decimal over the number of places that the 10 is raised to. So if I move it over 1, 2, I need to move it over 1 more. I'll need to put a placeholder to move it over that third decimal place. So an equivalence of 2.04 times 10 to the third would be a following number, 2040. In this next example, we have this number in scientific notation raised to the 7th power. When you have a positive exponent on your 10, it means that we have a large number. Your decimals will be moved to the right, and we only have enough for 4 places, and we need to move 7 powers of 10 on our number. That means we're going to have to put placeholders. Here was the first 2, here was the next 4, 5, 6, 7. So our original decimal place was here. There's 1, 2, 3, 4, 5, 6, 7 is the new place on our number, and this original number was over 19 million was the original number. This last example isn't in the best of standard form for scientific notation. It's an implied times 1. So we're now dealing with a negative exponent on our power of 10, which means we're dealing with a small number. And to put this in standard notation, we'll be moving our decimal place to the left. So here's our 1 with the implied decimal to the right of it. And since we have 10 to the negative 5th, it means we need to move it 1 power of 10, 2, 3, 4, 5 decimal places, which means we need to put zeros for our placeholders. And again, here's our 1, 2, 3, 4, 5 place values for the equivalent standard notation of this original number that's given in scientific notation. So our final answer would be, oftentimes we put a 0 in front of the decimal so that our I catches that decimal place, followed by 4 zeros and the 1.